All right, let's look at the homework from our related rates. For number 3, it says if y is equal to x cubed plus 2x and dx dt is equal to 5, find dy dt at the instant when x is equal to 2. All right, so let's go through step number 1. None of these were identified as constants. We've already got the equation that relates our quantities. So let's go through and take the derivative of both sides with respect to t. So the derivative of y would be 1. And then we have to use chain rule, apply the dy dt because we don't know what the derivative of y is because it was not in terms of t. Take the derivative of x cubed. The derivative of x cubed is 3x squared. And then applying chain rule, we don't know what the derivative of x is because it's not in terms of t, so we'll leave a dx dt there. Then take the derivative of 2x. That would be 2. Again, x not in terms of t, so we leave a dx dt in our problem. So we said the abbreviated practical version of that is take your derivative as normal, but you're going to need to leave a derivative in terms of t in for every single quantity after you take the derivative. So when we took the derivative of x cubed and got 3x squared, we also had to leave that derivative of x in terms of t in there. All right, now let's plug in the values that we know. We can go through and say, okay, x, they told me, was 2. So let's put 2 in the place of x. dx dt, they told me was 5. So we'll put 5 in the place of dx dt. And then, again, 5 in the place of dx dt. And so when we simplify, that gives us 70. All right, look at number 7. For number 7, it says, a street light is mounted at the top of a 15-foot tall pole. A man 6 foot tall walks away from the pole with a speed of 5 feet per second along a straight path. How fast is the tip of his shadow moving when he is 40 feet from the pole? All right, so here's our diagram where we've got our pole that's 15 foot tall, our man that's 6 foot tall, and he is walking away from the pole, so he's walking this direction, and his shadow would be cast out in front of him. And it says that he is walking at a rate of 5 feet per second. So I called the distance between the man and the pole x, and so that is increasing at a rate of 5. So the rate of change of x with respect to t would be 5. How fast is the tip of his shadow moving? Well, I called the distance of the shadow y so that we could see if we combine this total distance here, x plus y, then we could go through and say, okay, that would be the rate of change of the tip of his shadow. So the distance from the pole to the end of the shadow, we want to know the rate of change of that. And we want to know it when he is 40 feet from the pole. So when x is equal to 40. So the only things that we know are dx, dt, and x, and we want to know the rate of change of this total distance, x plus y. So I could go through and say these are similar triangles, here and here. The way I know they're similar triangles is they have this angle in common, and the man is at a right angle with the ground, and the pole is at a right angle with the ground. And if two angles of a triangle are the same as two angles of another triangle, their third angles would have to be the same as well. If all three angles are the same, they're similar and their sides are proportional. So we could say, okay, the height of the pole, 15, is to the height of the man. So 15 is to 6, as the base of the triangle is to the base of this triangle. So as x plus y is to y. So 15 is to 6 as x plus y is to y. If we cross multiply here, we'll get 15y is equal to 6x plus 6y. And then subtract 6y from both sides and divide by 9, and we'll have y is equal to 2/3 x. So if we put 2/3 x in the place of y, then we'll have the derivative of x plus 2/3 x. So that would be the derivative of 5/3 x. And the derivative of 5/3 x would just be 5/3. Derivative of that would be, also don't forget to put in your dx dt. So if we plug in the values that we know, dx dt is 5, and so we'll get 25/3 feet per second. Now, they were trying to be kind to you in this example by not giving you an elaborate equation. I almost think that confuses us more when we're looking at this and we're trying to come up with an equation that relates these quantities. You know, they just asked me to find the derivative of x plus y. I don't have a great big equation that it's equal to something else. All I had to do was find the derivative of x plus y. I can't find x and y at the same time. They had only given me information for x, and so that was why we used our similar triangles to replace y with an equivalent x, so that then we would just have the derivative of one quantity, and it was a quantity that we could utilize. So they're not trying to make it difficult for you here. They were trying to ease you into this instead of giving you a great big elaborate equation, but I almost think because we didn't have an equation in the beginning, it makes it a little harder for us to see. So let's look at number 9. It's a little more normal for us. For number 9, it says 2 cars start moving from the same point. One travels south at 60 miles per hour, so traveling south at 60 miles per hour. The other travels west at 25 miles per hour, so starting at the same point, and this one travels west at 25 miles per hour. At what rate is the distance between the 2 cars increasing 2 hours later? So the distance between those 2 cars I'm calling z, and it's increasing, and we want to know what it is at the instant that 2 hours have passed. So if we go back and say, okay, car A is traveling south at 60 miles per hour, so or car X, if you want to think of it that way. The first car, rate of change is its speed, 60 miles per hour, and that is an increasing quantity. It's getting larger, so that's going to be a positive 60. The other travels west at 25 miles per hour, so car Y, his rate of change is going to be a positive 25 because that's an increasing quantity. And we want to know the rate of change of the distance between them, so we're going to be looking for dz dt. That's going to be our unknown, and we want to know what that is when time is equal to 2 hours. Well, if car X is going 60 miles per hour, then after 2 hours, this distance would be 120, because rate times time is equal to distance. And if car Y is going 25 miles, or if this car over here is going 25 miles per hour, then the distance for Y after 2 hours is going to be 50. If I know 120 and 50, I could use Pythagorean theorem to figure out what Z is at that exact instant, right? So I could say 120 squared plus 50 squared, and that would give me 130 squared, so I also could find Z. Obviously, the equation that relates these quantities is Pythagorean theorem, so x squared plus y squared is equal to z squared. So if we go through and take the derivative of x squared is 2x, not in terms of t, so we'll leave a dx dt in there. Derivative of y squared is 2y, not in terms of t, we'll leave a dy dt in there. Derivative of z squared is 2z, not in terms of t, so we'll leave a dz dt in there. So let's plug in what we know. All right, so we know that x is 120. We know that dx dt is 60. We know that y is 50. dy dt is 25. Z is 130. And dz dt we don't know, but that's what we were trying to find. If by chance you had not thought to go ahead and find z up here, when you got to this point where you didn't know z and you didn't know dz dt, that would have prompted you to go find that z value. So now if we go through and simplify, we'll multiply here and combine those two values. And then over here, 2 times 130 is 260. To get dz dt by itself, let's divide both sides by 260, and we find out that dz dt is a positive 65. It is an increasing quantity, so it should be positive. And then remember that your label is just going to be whatever z was measured in over whatever t was measured in, so it'll be miles per hour. All right, look at 17. For number 17, it says water is leaking out of an inverted conical tank at a rate of 10,000 centimeters cubed per minute. At the same time, water is being pumped into the tank at a constant rate. The tank has a height of 6 meters and the diameter at the top is 4 meters. If the water level is rising at a rate of 20 centimeters per minute when the height of the water is 2 meters, find the rate at which water is being pumped into the tank. All right, so if it says that water is leaking out at a rate of 10,000 centimeters cubed per minute at the same time water is being pumped in, and we're trying to find the rate at which the water is being pumped in, that's going to be my unknown. C is going to be the rate at which the water is being pumped in. So if I take what's coming in minus what's going out, that's going to be the rate of change of my volume. Then it says the tank has a height of 6, so we've indicated that over here. And the diameter is 4, so if the diameter is 4, the radius would be 2. The water level is rising at a rate of 20 centimeters per minute. So that's going to be the rate of change of the height. So dH dt will be 20 when the height is 2. So when h is equal to 2. Find the rate at which water is being pumped into the tank. So here's that volume formula for a cone that we worked with yesterday. And if you'll notice, if I were to take the derivative of this as it stands right now, I would get a dv dt, a dr dt, and a dh dt. I have dv dt and dh dt. I don't have a dr dt, and that's not what I'm solving for. So I have got to get rid of r before I take the derivative. So if we come back to our similar triangles here, we discussed yesterday why this triangle and this triangle are similar and that their sides are proportional. So we could go through and say the radius is to the height as the radius is to the height. So we could say r is to h as 2 is to 6. So to get r by itself, multiply both sides by h, we would get 2/6 h, which would reduce to 1/3 h, or h over 3. So now I can replace the radius with h over 3. And now I can express my volume. H squared times h is h cubed, and 3 squared is 9 times the 3 that's already here is 27. I can express that volume in terms of the height only and not have a radius in there. So now I'm ready to take that formula and take the derivatives. So the derivative of v is 1, not in terms of t, so we leave a dv dt in there. And then here I have a constant times h cubed. So if we take that derivative, it's going to be 3 times pi over 27 h squared. So 3 pi over 27 would be pi over 9 h squared. H was not in terms of t, so we leave a dh dt in there. All right, so dv dt was c minus 10,000, so we can plug that in. And then h was 2, but if you'll notice in the problem, it's 2 meters. And my rates of change are all being measured in centimeters. So I made a note for you for this problem last night to be sure that you changed your 2 meters to 200 centimeters. So when we plug in our height of 2, we're actually going to plug in 200 centimeters here. So h squared. And then dh dt was 20. All right. So once we have all that plugged in, then we can go ahead and solve for c. So we can do 200 squared times 20 times pi, and divide that by 9, and then we just need to add that 10,000 over to the other side. And so that would be the rate at which the water was being pumped into the tank. Now that C, remember, if it's the rate of change of the volume, we need the volume in the numerator, whatever it was being measured in the numerator, and the time in the denominator. So our volume was being measured in centimeters cubed, and our time was being measured in minutes. All right, then for 23. For 23, it says two sides of a triangle are 4 meters and 5 meters in length, and the angle between them is increasing at a rate of 0.06 radians per second. Find the rate at which the area of the triangle is increasing when the angle between the sides of fixed length is pi over 3. All right, so here's our diagram. We've got a triangle where x is equal to 4 and y is equal to 5. So x is equal to 4, y is equal to 5, and theta is the angle in between them that's being measured in radians. And it says the angle between them is increasing at a rate of 0.06 radians per second. So the rate of change of theta is going to be 0.06. Find the rate at which the area is increasing. So I'm looking for the rate of change of the area when the angle, at the moment the angle is pi over 3. Now, if you're looking for area of a triangle, there were two formulas in the front of your textbook or on that formula handout that I gave you. The first one, of course, is 1/2 base times height, but there's a second formula there, which is 1/2 AB sine theta. Let me start with what if you used 1/2 base times height and how you could have gotten to this second formula, and